Okay, so I want to look at like a few summation formulas from last year, and so the I guess four summation formulas that you should know are if you're adding up consecutive like integers, squares, cubes, or just like constants. But some of the notation you might be a little bit either rusty on or unfamiliar with. Our book this year uses like I's, and maybe last year used K's. So even that sometimes makes a big difference. But looking at these four formulas, just adding up a whole bunch of numbers over and over again, right? That you just multiply whatever that value is times however many you have. So, if I said, for example, find the sum of I equals 1 to 10 of 3. In other words, that's telling me that I have 10 terms of 3, like 3 plus 3 plus 3 plus 3, 10 times. So you just do, 3 times 10, so that would be 30. Okay. Now, if you have like consecutive integers, and this is where last year in honors pre-calc, I know I talked about Gauss and how he was like 10 years old and was able to add up a whole bunch of numbers like right away, and kind of really made his fifth grade teacher really mad. So, but so like let's say I wanted to add up the first 100 numbers. I think that was Gauss's problem as well. So like I equals 1 to 100 of just I. Right? So that'd be like 1 plus 2 plus 3 up to 100. So if you know that there's 100 numbers, you just do 100 times 101 divided by 2, which, if you remember from last year, was 5,050. Okay, now adding up squares, right? So like if you want to add up the first, let's say 25 squares. So what that would look like is a sigma notation is I equals 1 to 25 of I squared. And then that would, since there are 25 squares, you do 25 times 25 plus 1, which is 26, times 2 times 25 plus 1, which is 51, all over 6, and get an answer for whatever that is. And then there's one for like every power, but the ones we'll see mostly will be those first three. Sometimes we'll see a cube. So the summation of cubes, let's say I wanted to find the first 10 cubes. That's I cubed. So then that would be 10 squared times 10 plus 1, which is 11. So 11 squared all over 4, and whatever that result is. Now, again, a key thing here is that your I is your index of your term, where N is the top, like is how many numbers you'll be counting up. And as long as you start at 1, then, N represents that value. Okay, so so for that first example, oops, sorry, I think I went too far. There it is. So it says, like, let's evaluate this for just different values of N. So like, if it said, okay, let's go I equals 1 to 10 of 2I minus 1. Remember, I would be your placeholder. So 1, and then you let it be 2, let it be 3, let it be 4, up to 10. So even if I really wanted to, I say, well, what does this look like? Well, if you let I equal 1, you get 2 minus 1, which is 1. And then that's sigma. And then you let I equal 2, and you get 3. And then you get 5. And then you just keep going all the way until you put 10 in there, which would be 19. So basically, it's like the first 10 odd integers. But since you know that there are 10 of them, so that's good. But you could also think about, like I could think about rewriting this as 2 times I equals 1 to 10 of just I, because that's right, breaking that up, minus I equals 1 to 10 of 1. And so now we say, oh, well, if there are 10 numbers here, that's 10 times 11 over 2, right? N times n plus 1 over 2 times 2 minus 10 ones. And so this would cancel, and you get 110 minus 10, which is equal to 100. So that would be our value for n equals 10. Now, n equals 20, same idea. So, like I would say, okay, so now we say, okay, I equals 1 to 20 of 2I minus 1. So then again, I could break that up into 2 times sigma I equals 1 to 20 of I minus I equals 1 to 20 of 1. And then again, you say, okay, there's your 2. And then it's 20 times 21 over 2 minus 20. And those canceled, and that would be what, 400 plus an additional 20, so 420 minus 20, which would equal 400. And, we could do one more just for, consistency's sake here. Let's let n equal 30. So sigma I equals 1 to 30 of 2I minus 1. That's 2. Sigma I equals 1 to 30 of I minus sigma I equals 1 to 30 of 1. And then again, there's your 2 from the coefficient. And it's 30 times 31 over 2 minus 30. 2's cancel. That's 930 minus 30, which equals 900. Okay. So again, just, practicing, I guess those would be the first two formulas, right? The summation of constants and then the summation of, consecutive values. Okay, so let's go ahead and look at example 2, and, we'll finish this video here. And what I like about example 2 is that we are throwing in this 1 over n squared. And remember, 1 over n squared is nothing but a constant once you choose what n is. I is the thing that's changing over time. So if I look at the summation, I can actually pull out that 1 over n squared if I wanted to. So like for n equals 10, so I could say the summation, maybe come over here more. 10. So I equals 1 to 10. So it'll be 1 over 10 squared, which I could pull out, times I. So it's like 1/100th times I equals 1 to 10 of I, which is just 1/100th. And it'd be 10 times 11 over 2, which is what, 55 over 100. And I mean that those are both divided by 5, so we can say it's 11/20ths. Okay, so let's try 100. And so if we go to 100, the sigma I equals 1 to 100, 1 over 100 squared times I. And so then we could pull that 100 squared out. So that's 10,000. Sigma I equals 1 to 100 of I, and then that would be 1 over 10,000 times 100 times 101 all over 2. And so remember, that was like 5,050 divided by 20,000. And again, you could certainly reduce that, simplify it, whatever. Okay, last one on this one, up to 1,000. And go purple, why not? So we get the sigma I equals 1 to 1,000 of 1 over 1,000 squared times I. And again, pulling out that would be 1 over, oh my goodness, million. 1, 2, 3, 1, 2, 3. Sigma I equals 1 to 1,000 of I. So you get 1 over 1 million. It's like $1 million times 1,000 times 1,001 over 2. And whatever that answer is, you could simplify that. Now, the whole point, what's happening here is that, as n gets bigger, obviously you go through more terms. But the fact that I put this coefficient in front, like 1 over n squared, that's going to get smaller very fast too. And so the more n's we get, like because this is getting smaller faster because it's quadratic, we start to level off. We start to converge to a certain value, which is going to be really, really important. Okay. So, really, this video had, like, I mean, you could take it out of context of calculus and it could have just been an honors pre-calc exercise. But we're going to see why we need to know and remember our summation formulas because they're going to help us basically count rectangles, right? And they help us count infinite number of rectangles because we've already looked at finding area under a curve using rectangles, right? Approximately, as a model to find area under the curve. But what if we could find an infinite number of rectangles and add up their areas? That's sort of where we're going with this. So, okay. I'll go ahead and pause this and we'll look at some more examples.